Yes.
Yes.
Okay, one thing I just wanted to ask all of you before I start the class, did you receive the link for the Google folder that I had sent in the morning today? All of you? Because we have the class test on
Yes, sir.
Thursday. So are you able to access that Google folder? If you click on the link, are you able to see that Google folder?
Yes, sir.
So anybody has any problem, he can tell me right away. I'll try to fix it. Because that day, yes, so you're saying something, tell me.
Like we are able to access we can like everybody else can edit everybody else's submissions. Is it so or like
No.
we
You
have
can only upload. You can only upload. I am the administrator.
Okay, yes.
You can only upload. Okay, as far
Yes.
as I know, because I am the administrator, I can only see everyone's thing, but you can see only your thing.
Okay, sir.
So you can check by uploading some file. You just try to upload something, and you can see whether you are able to see that file in that folder. You are able to download it and check it or not. Like that, you can just check.
Okay, sir.
Generally, it works. I have done it last time for my previous course, so this thing works.
Okay, sir.
If there is any problem, I will ask you to mail me. I will give you a mail ID. I will ask you to send your PDF file by mail to that time. That's it.
Okay,
So
sir.
we can use our personal email ID or the institute email ID.
I will give you my personal mail ID. Okay, my
No,
Gmail
sir.
ID.
So to open the folder, can we use our personal Gmail ID?
I think you have to log in into Gmail. Then only your Gmail ID is there. Na? Everyone has a Gmail ID.
Yes, yes, sir.
Yeah, so I think you have to log in into your Gmail ID. Then try.
Basically, sir, as per mine, with the institute Gmail ID, the folder is not opening, but with the personal Gmail, it is opening.
Okay, fine.
Okay.
So whatever it is possible to do, you can do. I just need to see the file in the folder. I will be looking at the folder while you are uploading it, and I will check the file once you upload, then put your attendance, okay, on that date of the class test. So after finishing your exam, you have to upload that file into the folder. I will see that file, it has come in the folder, then I will give you the attendance. Okay, that means you have actually appeared in the exam. Otherwise, I will not believe that you appeared in the exam. So you have to ensure that your file is visible in that folder. Okay? And if there is a problem that day, then I will give you my email ID. You can mail me your file. Okay, so I think let us start the class. So we were going to work out some problems and understand the properties of Z transform. So that is why I required a longer duration class today. So let me just recap that we are given two sequences, G of n and H of n, which have Z transform G of Z and H of Z. And the individual ROCs are ROC subscript G and ROC subscript H. That means for GZ and HZ, there are two different ROCs. They are denoted with ROC subscript G and ROC subscript H. Then these are the properties of the Z transform. So if you see linearity, the first property is linearity. And here you see like it becomes a linear combination of the two Z transforms. And the final ROC of the sum of these two sequences is the intersection of the ROCs of the individual sequences. So then again, time shifting property. Here you have Z to the power minus n naught into G of Z. Because of this Z to the power minus n naught, depending upon the value of n naught, whether it is positive or negative, you will have either the exception of Z equal to 0 or Z tends to infinity. So because this term appears here before G of Z. Similarly, scale change in Z domain or multiplication by a complex exponential in the time domain. So that leads to a scale change in the Z domain. So that is the idea here. Now you have time reversal. If you have time reversal, then you have the reciprocal of the Z here in G of Z inverse. So the ROC becomes 1 by ROC of G of Z. So ROC of G of Z inverse is the reciprocal of the ROC of G of Z. Time expansion, here like you are doing actually dilation of the signal by dilating it by a factor, and n by k, k is the dilation factor. So the Z domain becomes G Z to the power k, and like all these properties we have already seen, and we are going to work out some of the problems today. And here you see this is important Z domain differentiation, which is like multiplication by n in the time domain. So negative sign is here, the negative sign actually comes here. N into Gn, that has the Z domain equivalent of minus Z into d by dz of G of Z. Conjugation is pretty simple. Here, this is the most important property, convolution, and we will derive all this G of n minus G of n minus 1, first backward difference. This is actually the differentiation of property in the time domain, and this is actually a discrete differentiation. And similarly, you have accumulation or discrete integration in the time domain. So for that also you have the Z transform, and you will see that this becomes a convolution of U of n with G of n. All that we will see today. The initial value theorem and the final value theorem, you will see that there is a lot of correspondence between Laplace transform and Z transform. So Z transform is very closely connected to Laplace transform. Laplace transform is for continuous time signals, and Z transform is for discrete time signals. Just I want to understand from you whether you have gone through Z transform in control systems or not. Have you done Z transforms in control systems? Generally, control systems in digital control or even in control 1, you are taught Z transforms for discrete signals. Have you done? Anyone?
No, sir. We didn't have any digital control.
But even normal control, you were taught the transient response of second order system. Those things you were taught. Transfer function.
Yes, sir. For a normal thing, it was taught, not in digital.
But you were taught all that in continuous time domain. Nothing in Z domain.
No, sir. We were not taught in digital domain.
So you never went through Z transforms, neither in the signals and networks course.
No, sir.
So this is, you are getting exposed to Z transform for the first time here. Is it like
Yes, sir. First time.
all the UG students? Is it like that? Yeah, so then it is little difficult for you because I was thinking of teaching one more chapter on Z transform, but I don't know how much time I have. We'll see if I have time towards the end of the course. Then I'll come back and teach one more chapter on Z transform, that is application of Z transform to discrete time LTI systems. So that is something that I'm not going to teach right now. I'm keeping that pending. So I'll just introduce the idea of the transfer function in the Z domain, or the system function as it is called, h of Z, and the analysis of behavior of discrete time LTI systems due to the position of poles and zeros of h of Z. That I will keep it pending because I don't know how much time I have in this course. So let me see. So let us start looking at the examples to illustrate the properties of Z transform. So the first example is linearity. So x of n is the sum of two causal sequences. Okay, I have taught you the bilateral Z transform of two-sided complex exponentials. That means I have taught you how to take the Z transform of causal plus anti-causal signal, and we have seen that the ROC turns out to be an annulus. So last class we had discussed all that, but here you see these are like two causal signals, right-hand side signals. So 2 to the power n u of n and 3 to the power n u of n. So they have Z transforms as 1 by 1 minus alpha Z inverse. This is the formula that you're going to use. So 1 by 1 minus 2 Z inverse and 1 by 1 minus 3 Z inverse. Individually, the ROCs are mod Z greater than 2 and mod Z greater than 3. So the intersection of the ROCs is mod Z greater than 3. So the sum of these two sequences, the ROC or the Z transform of that sum is mod Z greater than 3. Are you able to understand what I just said? See, ROC, we are generally worried about the poles, not about the zeros. Okay. So if you look at this, you expand this 1 by 1 minus 2 by z, and here 1 minus 3 by z. So you will get two poles here, z minus 2 and z minus 3. So there will be two poles at 2 and 3. Okay. And there will be two zeros at the value 0 and the origin. Okay, so we are worried about the convergence of the Z transform. So we are only worried about the poles, because at the pole the ROC as the Z transform doesn't converge. Z transform goes to infinity. So the ROC will be mod Z greater than 3. Is this clear to everyone?
Yes, sir.
So let us see another one. Here we will use time shifting in the consonance with the linearity property. So here we have a finite dimensional or finite duration signal. So it is 1 for capital N samples. Okay, and going from 0 to n minus 1. So for capital N number of samples, this is having a finite amplitude which is 1, and it is 0 otherwise. So if you want to find out the bilateral Z transform, because the bilateral Z transform now will become a unilateral Z transform. So it will go from 0 to infinity or 0 to n minus 1, because on the left hand side the signal is 0. So you will have causal finite duration, finite amplitude signal, which is this. And if you use the geometric progression formula, then you get this formula. You can derive this by using an idea here that xn can be written as u of n minus u of n minus capital N. Okay, so you know the Z transform of this guy, and you know the Z transform of this guy. You can derive the Z transform of this guy by knowing this fellow. So here you know u of n minus n time shifting property, u of n minus n naught, that is z to the power minus n naught into g of z or u of z. So here it comes z to the power minus capital N u of z. U of z is 1 by 1 minus z inverse. Okay. You have alpha to the power n u of n. If you keep alpha as 1, then you get u of n. So alpha to the power n u of n has the z transform 1 by 1 minus alpha z inverse. So here it will be 1 by 1 minus 1 z inverse. That's it. And the upper term, the numerator, comes from this 1 minus z to the power minus capital N. You can all see my cursor, right? The mouse pointer you can see.
Yes, sir.
Yeah, so you can see how simply we have derived this. Even without using this sum, we can derive this sum by using the properties of linearity and time shifting. These are two important properties. People have a habit of coming late. Even at 6 o'clock they come late. Okay, so now another property that is clear, I think, for all of you. Previous example. If somebody is writing, then he can write. I can wait for some time. Actually, with DSP, we should have a DSP tutorial. I don't have a tutorial. So whatever time I can devote to some of the examples, that's what I'm giving. I cannot do so many problems because we don't have a separate tutorial class. So this is troublesome, but I'm still trying to do as many examples as possible to illustrate the ideas.
Sir, ROC is except Z is equal to 0. So
Yeah, ROC is the entire Z plane except Z equal to 0. See, because Z equal to 0, if you put here Z to the power minus m, 1 by Z to the power m, then it tends to infinity, right? Got it, nah? This is 1 by Z to the power m. If you put Z equal to 0, then this whole thing blows up.
yes, sir. But from the second, I mean, the last part, from that, can we be able to find the same ROC?
Yeah, you can try. You can try to analyze this. Try to analyze this. Because finally you are going to get this.
That is, yes, sir, that is okay.
Okay, so the next property, differencing in time domain. So that is what I was trying to show you there. G of n or something like delta of n minus delta of n minus 1. So delta of n is the Kronecker delta. So when you do this operation, you are actually taking the difference of two consecutive samples of x of n. So when you do, suppose h of n is the impulse response of a discrete time LTI filter, the impulse response is given like this. Okay. And you are trying to convolve that impulse response of a discrete time system with a sequence x of n. So what that system is doing is actually a differentiation operation in the time domain. In the discrete time domain, it is a differentiator. So this operation is a linear operation. Convolution operation is a linear operation. So you can find out the Z transform. For Z transform for delta of n is 1, and here it is shifted delta. Therefore, you will have Z to the power minus 1. Delta of n minus n naught. N naught is equal to 1. So Z to the power minus n naught into G of Z. That is Z to the power minus 1 here. So ROC is equal to the entire Z plane except the origin. Again, because of this guy. Also, the Z transform has a 0 at Z equal to 1. So if you just simplify this, you can understand that there is a 0 at 1. So like this is a differentiation operation that is going on in the time domain. So let us see what happens when you do this thing in the time domain. You are able to get x of n minus x of n minus 1. So this is actually a first derivative operation in the time domain. Okay. I think I've taught you this while I was doing DTFT, right? The difference operation, the forward difference, the backward difference, we have seen this. There are two formulas to calculate numerically the differentiation of a sequence or signal in the discrete time domain. So you are given a time series or a sequence in the discrete time domain, and you want to calculate the derivative, the first derivative. So you can use the forward difference or the backward difference formula, and you can calculate the differentiation. So this is the discrete time counterpart to differentiation of continuous signals. Okay. So y of n will be like this. The Z transform will be 1 minus Z inverse into Xz. So the Z transform of this fellow or the discrete time system or the differentiator is 1 minus Z inverse. This is also called the system transfer function. We will come to that. H of n is the impulse response. H of Z is the Z domain equivalent of that, and that is called the system transfer function. Is this clear? Yes, sir. Whenever I am using this kind of a double arrow, it means that y of n is being taken into the Z domain by using this operation of the Z transform. This side is Z domain, this side is time domain. So now the discrete time counterpart of integration, so we call it accumulation in the discrete domain. So you are actually doing a running sum. You are accumulating a signal. So if the signal exists from negative infinity to positive side, then you are doing an accumulation of this. You are actually doing a cumulative sum. That is the technical term. So you are cumulatively like adding up the sequence values or the amplitudes of the signal. So this entire operation can be treated as a convolution of the unit step function in the discrete domain convolved with x of n. Okay. That is the important idea here. So u of n convolved with x of n. So again, we can use our property of the z domain. That is, you can take the product of u of n, the u of z, and x of z. So u of z is 1 by 1 minus z inverse and into xz. So the z domain equivalent is this for the accumulator function. So again, the ROC will be the intersection of the ROCs of x of z and 1 by 1 minus z inverse. 1 by 1 minus z inverse ROC is mod z greater than 1, and the ROC of this guy is R. So the intersection of R with mod of z greater than 1. That will be the ROC of this entire the left hand side. Entire right hand side. So this is the z domain equivalent of the continuous time integration. So these are important ideas that we are learning right now. So when we build systems, we will be using differentiation, integration, left and right. So we need to know what is the z domain equivalent of all this. All this would have been taught to you while you were doing signals and networks Laplace transforms. Okay. So in the continuous time domain, all this would have been taught to you. You can open up your previous notes and you can refer to that Laplace transform. So we have done differentiation in the time domain. We have done an accumulation in the time domain. Let us go to the z domain. So differentiation in the z domain. Okay. So we want to find out the z transform of this signal. So it is n times x of n, where x of n is equal to a to, or x1 of n is equal to a to the power n u of n. So we already know the z transform of this guy, that is 1 by 1 minus a z inverse, mod ROC mod z greater than mod a. So then we want to find out what is the z transform of n into x1 of n. That is the problem. So if we use the z transform property, then n into x of n has a z transform minus z into dxz by dz. That is differentiation in the z domain. So in the z domain, we have this polynomial or the rational function. So I want to take the derivative of this guy with respect to z. That turns out to be this much. ROC mod z greater than mod a. So if you set a equal to 1 here, then you get this nice expression, that is the differentiation in z domain of the unit step function. It is actually a unit ramp signal, or the z transform of the unit ramp signal. N into u of n is a unit ramp signal. If you plot it, it will be like a ramp in the discrete domain. It is n for u n to u of n. So the signal is a linear signal, and it is just like a ramp in the on the right hand side of the coordinate system. Is this okay? So we have derived this formula now that this is equal to this. This is differentiation in the Z domain. I can do very limited examples. Okay, you please start looking at Oppenheim Schaefer and other books like Prokis Manolakis for DSP. Even BPLRT has many examples. So can I now go to the next slide?
Yes, sir.
I see there are almost 30 students bunking. So that will show up in the exams. Okay. So one more example. So xz is given as log of 1 plus az inverse. Mod z greater than a is the ROC. You are supposed to find out the inverse z transform. That means you are supposed to find out what is x of n. So again, we will use the property of differentiation in Z domain to derive what is x of n. This is a very nice example, not so easy, not so trivial to derive. It requires some thinking. So we are going to use this property. So we know this property of dz transform. So we are first going to find out what is d by dz of xz. Xz is given to you. Our problem is to find out x of n. We know this property. So we are going to use this property. That means we are first going to find out the derivative with respect to z of xz. That turns out to be this guy. All of you, please work these things out. Okay, don't take me on the face value. You should verify whatever I'm showing you. If you want to stop me anywhere, you can stop me and ask me. Is it done? So let me go to the next step. So using a linearity property, you can write this thing out. Okay. So you know what is a to the power n u of n z transform. So you can write what is this guy like this. And you combine this with the time shifting property. That means you change n to n minus 1 here and here. So it becomes a into minus a to the power n minus 1 u of n minus 1. So n minus 1 means you will get an additional z to the power minus 1 term here on the right hand side. So that's what comes here. Okay. So this is appearing on the right hand side. Now you see what was your x of z? Your x of z was given like this. And now this guy is dxz by dz. Okay. Compare this guy. Or minus z dxz by dz is equal to actually this. This is this only. So on the left hand side we had this, and on the right hand side we have this. This is equal to this, given x of z here. That turns out to be this guy. So whatever comes on the left hand side is equal to n times xn. Is it not? This guy is supposed to be n times xn. Because on the left hand side here is n times xn, and on the right hand side this is equal to this fellow. And here we already have got this. So xn becomes 1 by n into this fellow. This can be simplified with this. This can be simplified like this. You try to derive this from here. It is not so easy. Little bit of thinking is required. Try to derive this fellow from here. X of n is just 1 by n times this guy. Are you understanding what I am saying?
So there is an extra negative in equation 10.9.
That is correct. You can derive it out. That is correct. It's not wrong. You can derive this expression from here. Right. It is not wrong. It is correct. All of you try. Try to derive this guy from here. You see how tricky sometimes the problems can be. This is just something that I'm just showing you. There are so many problems in the book. You open and Shepherd. There are so many problems. So by using the Z domain differentiation property, we can find out what is x of n for this guy. So we can do inverse Z transform by using the property of Z transforms. That is something to understand from here. So we have derived the inverse Z transform of this guy. We'll come to inverse of Z transforms in the next part of the just next class, I think. Next week we'll do inverse Z transforms. But it's just to tell you like how using the tables of properties of Z transform we can find out the inverse Z transform. Is this example clear to everyone? Is there any doubt? Please ask me. Today I am going very slow.
Yes, sir.
So everyone please try to derive this final expression from this guy. It is just one step. Okay. So this is differentiation in Z domain. We have seen differentiation in time domain, accumulation in time domain, now differentiation in Z domain. Now let us see. So if you are comfortable, then shall I move ahead? Okay.
Yes, sir.
So derivation of convolution property. So proof, how to derive this. So all of you can see the slide. Is it clear? So here there is an interchange of the order of summations just to facilitate the derivation of the two Z transforms, and we are using here the property of time shifting. So this is x2 of n minus k. So if you take the Z transform of this will be Z to the power minus k into x2 of Z. So Z to the power minus k comes here and x2 of Z comes here, and you can bring summation of k equal to minus infinity plus infinity x1 of k into Z to the power minus k. So that leads to x1 of Z. So this is a derivation of the convolution property. So from the convolution property you can derive this. Just take a look at the expression here, because we are going to also derive the formula for the correlation between two sequences. So in the convolution formula, the index of summation is k, and k is the shift here. Can you see this?
Yes.
Yeah. If you have made a note of this, then we'll go to the next slide, which is the correlation slide.
Hello, sir.
Yes.
Sir, in the second half, upon changing the order of summation, that I understand, but where is the time shifting property applied?
Here, x2 of n minus k. x2 of n minus k, you are taking the Z transform here. Is it not?
Acha, yes, okay. Thank you, sir.
Today I'm going very slow. You can ask me questions. Actually, I should be speeding up. This course is lagging a little bit. I have missed some classes. Okay, this is clear? Okay. Let us come to correlation. So if you compare the formula of convolution and correlation, there is something which is going little tricky. You see here, the index for correlation is the lag, L. And you are summing over all n. The lag is here. Whereas here in the convolution, you are summing over k. And here comes out x of n. So this is connected, the convolution is connected with correlation in a simple way. That idea is here. So correlation is convolution with one of these sequences flipped. So x1 of L convolved with x2 of minus L. So if you apply the formula for convolution with this, you are going to get back this guy. You can try to derive this out. Whatever I am saying, don't believe me. Try to prove that this formula is convolution of x1 of n with x2 of minus L. Whatever I am asking you to do, please you do it, work it out yourself. Unless you work it out with pen and paper, you will not understand what I am saying. There is a difference between computer science and electrical engineering. Okay. Computer science, you directly type on the keyboard. Electrical engineering, you have to write on paper. I rate computer science much lower than electrical engineering. Electrical engineering is a hard science. It is difficult to digest so many concepts in 4 years. Computer science you can complete in 2 years. If you're a good student. Whatever they study in 4 years, you can complete in 2 years. Okay, so we have this formula here because we are convolving with x2 of minus of n, or so we have x2 of z inverse using the property of negative n. X of n has x of z inverse. So this is simple correlation convolution. Is it okay, everyone? So we have seen several examples using the properties of Z transform. So let us come to the idea of rational Z transforms. So when you see Z transforms in the problems and all, generally you will see that there is a numerator and denominator. So we have like x of z, which is given to you, which is a rational function, that is, it is a ratio of two polynomials. And those two polynomials can be in z inverse or in z. So we can write x of z as the ratio of two polynomials in z, b of z and a of z. So if you equate b of z to 0, then you get the values of z for which x of z is equal to 0. If you equate az is equal to 0, then you get those values of z for which x of z is equal to infinity. So for the previous case, you get the values of the zeros of x of z. And for the second case, if you put z equal to 0, then you get the poles of x of z. So based on this formulation, we will look at the transfer function and then think about FIR filters and IIR filters. So like Z transform is the most important like call in DSP. From here, your discussion about filters and design of filters starts. And I should teach you one more chapter, which is application of Z transform to LTI systems. So there you will understand the behavior of an LTI system response, or the transfer function on the location of poles and zeros. That is a very important part. I'll see if I get time, how much time I get. I'll bring that concept. So if xz is a rational function, you can write it in terms of the ratio of two polynomials. The polynomials can be in terms of z to the power -1, that is like this, or you can simplify it by taking two factors out from the numerator and the denominator. So you can take out b0 into z to the power -m from the numerator and a0 into z to the power -N from the denominator. And you can create these two polynomials in only z, not z inverse. Okay. This has maximum power capital M, this has maximum power capital N. Now, depending on M relationship with capital N, you get a proper rational function or an improper rational function. So if M is less than N, then you get what is called a proper rational function. So if M is greater than N, then you get what is called an improper rational function. These are some terminology that you should know. I'm just telling you these things out. Those who are making notes, they can write down. Depending upon the relative values of M and N, you get a proper rational function or an improper rational function. Generally, we try to bring our x of z in the form of a proper rational function, not improper. So generally, our capital M will always be less than n. Otherwise, we have to divide and bring it down. We have to divide the numerator by the denominator and bring it down. Convert an improper rational function into a proper rational function. Okay, done. Okay, let me go to the next slide. So here you will have these polynomials can be factored. So you can factor them, the numerator and the denominator. You see Z1, Z2 up to Zm are the zeros of xz, and P1 to Pn are the poles of xz. So these are polynomials in Z, so we can factor them out and you can create or you can find out the zeros and the poles of x of z. So finally you will get a simplified form of x of z. This is the rational function. G is equal to b naught by a naught here, z to the power n minus m. So xz has m finite zeros, z1 to zm, which are the roots of the numerator polynomial, and n finite poles at p1 to pn, roots of the denominator polynomial, and n minus m mod zeros, if n is greater than m here. These are zeros at origin. Or poles if n is less than m at the origin, z equal to 0. Okay, this stands for either poles or zeros at origin. A pole or a zero may also occur at z equal to infinity. A zero exists at z equal to infinity if x of infinity is equal to 0. And a pole exists at z equal to infinity if x of infinity is equal to infinity. This is from the definition of a zero and a pole. So if there is a 0 at z equal to infinity, then x of infinity will be 0. And if there is a pole at infinity, then x of infinity will be infinity. So if you count poles and zeros at zeros and infinity, then you find that xz has exactly the same number of poles as zeros. This you should understand. So always every xz has the same number of zeros and same number of poles if you include the poles and zeros at 0 and infinity. You will understand the utility of what I am telling now when we will try to do inverse of the Z transform using partial fractions. So then all this will start to become clear. So you have done this, you have written this down. Shall I go to the next slide?
Yes, sir.
Let us look at some plots with poles and zeros. Let us look at some of the transfer functions. So we determine the pole zero plot of this signal x of z. We will bring this in the form of a polynomial in z. So this is the numerator polynomial, this is the denominator polynomial, this is the rational function. The ROC is mod z greater than a. Where are the zeros in the poles? There is a 0 at origin, z equal to 0, 1 0 at z equal to 0, and 1 pole at a. And the ROC does not include the pole. This is why it is mod z greater than a, not greater than equal to a. Please make a note of this. ROC is mod z greater than a. This is a causal signal. It exists only for the right side. A to the power n, u of n. It is not including the pole. So ROC never includes the pole. Pole P1 equal to A is not included in the ROC because the Z transform does not convert at a pole. It becomes infinite at the pole. This is the pole zero plot for a causal exponential signal. So we'll jump from here to the next example. That is very interesting. Before I bring the next example, we should be understanding these ideas, how to plot poles and zeros. How to think about a rational function. So let me come to the next slide. Once you are done with this. So ROC includes the zero. That you should understand. That there is no harm in the zero being inside the ROC, but the pole cannot be inside the ROC. So let us look at this function. This is an exponential a to the power n, which is having a finite duration, n greater than 0 to m minus 1. So it is an m point discrete signal derived from an exponential where a is greater than 0. So it is something like a decaying exponential. For example, a is greater than 0, suppose a is less than 1. Then it is a decaying exponential. If a is greater than 1, then it is an infinitely increasing exponential. Let us say that it is a is greater than 0. Now, who is coming now, Baba? After 1 hour, somebody is coming. Okay. So by using the definition of the Z transform, we can find out x of z. And using this formula, you can write this out. So you see here, there are some interesting things happening. There is a numerator which has these roots. It has m roots. There are m roots in the numerator. And if you make a equal to 1, then those m roots are m roots of unity. Okay? I think you have already studied 3 roots of unity, 1 plus omega square equal to 0. I think you have studied that, right? During your plus 2, you must have seen that expression. And you see at the denominator, there is a 0 z naught equal to a, which cancels the pole at z equal to a. Okay. Something interesting is happening here. There is a pole at z equal to a. There is a 0 at z equal to a that cancels this particular pole. So the equation z to the power m equal to a to the power m has m roots, and you can find out those roots like this. This example will be connected when I talk about finding the roots or finding n roots on the unit circle. Then we will be using this to find out what is called the discrete Fourier transform. I'll come to that when I talk about DFT. in that chapter, but this example is very important. This gives you an idea. Like what can we do with the Z transform ROC? Okay. In the complex plane, what can we do? So there is a 0 Z not equal to A, which cancels the pole at Z equal to A. So we can finally write something like this. It has M minus 1 zeros and M minus 1 poles. If you see here, this particular pole is cancelled by one of the zeros on the numerator. So you will have M minus 1 zeros in the numerator, and this particular term will remain, that is M minus 1 poles. So M minus poles will be located at origin. And therefore, the ROC will exclude the origin. ROC is the entire Z plane except Z equal to 0, because the M minus 1 poles are located at the origin. So for M equal to 8, so in the book he has plotted the location of the poles and the zeros. And the radius of this circle is A, because you are trying to find out the roots like this here. The radius is A. So the zeros are placed on the circle of radius A and the poles are at the origin. Now what happens due to a pole zero cancellation? What happens in the frequency domain? All are very serious concepts. So I'm not touching on that right now. So I hope I can get time to talk about those things when I discuss like what is the behavior of an LTI system frequency response due to the location of poles. If I disturb the location of poles inside the ROC, what happens? I mean, inside the Z plane, what happens? Those are very serious concepts. We'll see whether I get time to discuss about them. This is some example which I just wanted to show you so that you can get an idea what happens to the when you are sampling on the circle of the ROC. And what was I saying? Yeah. So suppose this particular circle is the unit circle, and you are calculating the n roots on the unit circle, then you can use them to find what is called a discrete Fourier transform. So this example will again come there.
Hello, sir.
Yeah. Tell me.
Sir, there wouldn't be a sorry, just a minute. There wouldn't be a 0 at the positive side of the real axis, right?
0 is at equal to this one. This one gets cancelled off. Okay.
Yeah, actually, it was showing in the diagram. That's why I got confused, sir.
It will get cancelled off.
Yeah. Thank you, sir. Thank you, sir. Understood.
Okay. So let us go to the next topic, which is system function of an LTI system. Till now we have discussed about XZ. Okay. If I have a sequence X of n and I want to find out its Z transform, then we can have something like a ratio of two polynomials. Maybe, may not be. Okay. You can have just only the expression without any denominator. But suppose you have a rational function in Z or Z inverse, then it has some nice properties. So that is one family of Z transforms of X of n. Now we will try to discuss about the Z transform of an LTI system or the Z transform of the impulse response of an LTI system. Of course, a discrete time LTI system. So the properties of the system can be described by looking at the poles and zeros of this guy H of Z. That is why we are trying to analyze H of Z by taking the Z transform of the impulse response of an LTI system. So on the left hand side you have the Z transform of the output of the LTI system. On the left hand side you have the input going in. This is the formula by using the time domain convolution formula. This is the Z domain equivalent. So y of n is equal to h of n convolved with x of n, and in the z domain it is capital Y of z equal to h of z into x of z. So h of z is known as the system function or transfer function of the system. Transfer function in the z domain. You can have a transfer function in the s domain also. So we are now talking about the transfer function in the z domain. So typically we call it as a system function. So if z is evaluated on the unit circle, that is if you put z equal to e to the power j omega, then h of z reduces to the frequency response of the system. That means you are calculating h of e to the power j omega. Okay, this you do for DTFT. So the frequency response of the system is also very useful because that gives you an idea about how the system behaves with different frequencies. So if you calculate h of z on the unit circle, provided that the unit circle lies inside the ROC, then you can calculate the frequency response of the system. So the general thing is system function that may or may not include the unit circle. But if the ROC of the system function includes the unit circle, you can also calculate the frequency response of the system. Okay, I hope this is clear. The general thing is Z. Z is equal to R into e to the power j omega. R may not be 1. Okay. If the ROC includes the unit circle, then you can put R equal to 1 and calculate what is the h of e to the power j omega. That is the frequency response of the LTI system. So given any impulse response, h of n, you can transform it into the z domain, you will get h of z. And if the z domain has an ROC which includes the unit circle, then you can calculate the frequency response of the system also. That is the idea here. So if the input to an LTI system is a complex exponential, that is x of n equal to z to the power n, then the output will be h of z into z to the power n. This h of z is called the eigenvalue. Okay, now you understand why this is called an eigenfunction. So z to the power n is an eigenfunction of the system with the eigenvalue given by h of z. So z of n appears unscathed at the output. If you feed z to the power n as an input, it will appear again at the output without change. Only thing that will change, the only thing that will get modified is by the application of this guy h of z. So h of z is something like an eigenvalue. So if you have something like x of y is equal to, or what is it, a into x is equal to lambda into x. So your a is something like a discrete time system, and or something like a matrix which describes a discrete time system. So you are feeding x into an LTI system, and that appears as lambda into x. So if there is an LTI system which is described by the A matrix, so you are multiplying A matrix with x on the left hand side. So that means you are transmitting a signal through an LTI system. That is, you are doing a convolution operation of x with the impulse response of the LTI system. The impulse response of the LTI system can be thought of as a matrix A which multiplies x to get you an output which is equal to lambda x, and that lambda is equal to h of z. Am I clear? Whatever I am saying, are you able to understand?
Yes, sir.
So this is the concept of eigenfunction. So the problem with like the UG guys is that they generally don't do DSP after doing signals and networks. They think that, okay, this course is over, huh? And there are so many concepts in DSP that you actually miss. And unfortunately, I was advised by one of my faculty colleagues that I should discourage the students from coming to my course because signals and networks for them it is a repetition. I don't know how many of you have understood the idea of eigenfunction before you read this sentence on my slide. Okay, this is coming in the Z transform chapter, and you are all telling me that we have never been exposed to Z transform. So properties of this LTI system can be tied directly to the characteristics of poles, zeros, and ROC of the system function. Now this is a very, very deep concept which I don't know whether I will have time to cover, but I will try to cover. So it's a full chapter If you look at some books, which are some classic books, they devote a full chapter to this. So those who are interested, please make a note of this sentence and make sure that you understand what this sentence means. All of you must read Oppenheim and Schaeffer. There are so many concepts in that Oppenheim and Schaeffer book. Unfortunately, the book is written in a very bad way. The font is very small. There is no spacing. It looks very daunting to read. But please get down to reading that book. Particularly that Z transform chapter, it is beautifully written. It is a very short chapter, but so many concepts are there in the first two chapters. So is it done? Shall I go to the next slide? Yeah, everyone.
Yes, sir.
So the important idea of expressing a convolution or rather a input-output relation between for a LTI system. How to write that expression for a discrete time LTI system? What is the input-output relation? That is given by what is called LCCDE or linear constant coefficient difference equation. So I hope you are all understanding what I am trying to say. This should have been taught to you in your signals and networks course. So we want to use that LCCDE, that difference equation, relating x of n and y of n, which is actually a convolution expression written in terms of a difference function, and we want to derive the system function, that is we want to derive h of z. Okay. So first we will write out that linear constant coefficient difference equation, LCCD, and from there we will take the z transform the left hand side and the right hand side and derive h of z. So how do we go? So h of z is actually the z transform of the impulse response, h of z n. So h of z is called the system function, h of n is called the impulse response. These are the two terms. So generally we write the output by relating it to the input like this from an LTI system. So if you find out the z transform of both the sides, then you can derive h of z as equal to y of z divided by x of z. So this is the linear constant coefficient difference equation. So if you apply the time shifting property, then you can simplify this like this. So I hope you have written this down. Okay, shall I go to the next slide? So you can simplify the above expression like this, and finally you arrive at the rational function expressed in terms of ratio of two polynomials in Z inverse. So this expression is important. So again, you can factorize this polynomial and these polynomials. So you will get roots of this as the poles of h of z, and the roots of the numerator as the zeros of h of z. And you can analyze the ROC of h of z, and you can think about the poles and the zeros, their positions, and then you can think about the causality and the stability of the LTI system. Okay, so we are worried about as system being causal and stable, because we want to realize those systems in practice. We want to build filters. H of Z means filter. So for electrical engineer, H of Z means a filter. Okay? So we want to build filters. So how will you build filters? What kind of filters will you build with this system function? So how will you think of an FIR filter? How will you think of an IIR filter from this expression? That is the important idea, what I am trying to drive now. Once you are done, please let me know. So I go ahead to the next slide.
Yes, Ranjan.
So an all zero system, which is also called a finite impulse response filter or a moving average filter. So if you put all the denominator terms 0, then you have only the numerator. And in the numerator, you have these. You can simplify the numerator like this. So h of z will contain m zeros, whose values can be determined by the system parameters bk. So bk gives you the zeros. There is an mth order pole at the origin. Okay, this one. And the system only contains trivial poles at z equal to 0 and m non-trivial zeros. This is called an all zero system, and it is also called a finite duration impulse response system or a moving average system. So these BKs, they are giving you the information about the zeros. So it doesn't have any non-trivial pole, only trivial poles at origin. this is the idea of an FIR filter. So you are bringing this idea from this guy. So if you put all AKs as 0, then the above equation will reduce to this form only, which is a form for the system transfer function or system function of an FIR filter. And it has m non-trivial zeros. So because it doesn't have poles at finite locations, therefore it is always stable. Okay. So this is something that we will look at. The FIR filter is very advantageous. Okay, fine. Shall I go ahead? So if dk is equal to 0, then the system function reduces to this form, and you are assuming that a0 is given as 1. So here h of z consists of n poles whose values are determined by the parameters ak. There is an nth order 0 at the origin, that is here, z to the power n, that is nth order 0 at the origin. So we generally don't bother about these trivial zeros. So this system contains only non-trivial poles whose locations are specified by this AK, and this system is called an all-pole system. So due to the presence of poles, the impulse response of such a system is infinite in duration. So this is an IIR system. So we have now two forms of filters, because h of z denotes an LTI system, which is something like a filter, because you are always going to pass an x of n through this h of n, and you are going to get an output y of n. So if you take the z transform of the convolution, then you get y of z equal to h of z into x of z. H of z can be written as a rational function, and that rational function can be further simplified as only the numerator or only the denominator. So if you have only the numerator of the rational function, then it is an all zero system, or a moving average system, or an FIR system. And if you have only the denominator, then it is called the all-pole filter. The all-pole filter is more popular in signal processing literature because of many reasons. If you do the course statistical signal processing, you will understand why all-pole filters are used. Just to give you some idea, our vocal tract can be considered as an all-pole system. So whenever I'm speaking, my vocal tract can be modeled as a filter, and that filter is modeled as an all-pole system, not an FIR system. And the sequence that is coming in is the gusts of air, and output is voice. Voice can be either consonants, or they can be vowels, they can be various things. I'm using various combinations of consonants and vowels and various other things to produce speech. And human audio can be thought of as being produced by a convolution of the input signal and an all-pole filter. So this is just giving you some example. Signal processing is very rich, and it can be broadly classified into one-dimensional signal processing, that is speech signal processing, and two-dimensional signal processing, which is image processing. So in both image and speech processing, you use all-pole filters. So this is not something to be thrown away, even though there are concerns of stability here because there are poles. And although it has an infinite impulse response, still all-pole filters are very popular. So let us come to the concept of causality. So just like a causal sequence, which is non-zero for n greater than 0 and it is 0 for n less than 0. Similarly, an LTI system which has an impulse response h of n that is 0 for n less than 0 and is right-hand sided, that is called a causal LTI system. So then the ROC of h of z will be the exterior of a circle in the z plane. Because for causal sequences, we know that the ROC is z greater than mod a. Mod z is greater than mod a. So ROC of h of z is the exterior of a circle in the z plane. So a discrete time LTI system is causal if and only if the ROC of its system function is the exterior of a circle, including infinity. So this is the idea of causality. So you see, like, we need to think about the z domain of or the z domain equivalent of the impulse response to talk about the causality of the system. So now we have another point here. A discrete time LTI system with a rational system function h of z is causal if and only if the ROC is the exterior of a circle outside the outermost pole. Okay, the outermost pole. The ROC cannot include any pole, so the ROC must exclude the outermost pole. And the h of z can be expressed as a ratio of polynomials, that is, it is a rational function in z. The order of the numerator cannot be greater than the order of the denominator. That is what I was saying, that it should be a proper rational function.
Hello, sir.
Yes.
I think it has stuck, sir, PPT.
PPT is stuck.
Yeah.
Can you see it?
Yes, sir. Now it's. I thought my system was stuck.
Everyone, can you see this slide? Could you see the previous slide?
Previously, I did not able to see, sir. Now it's okay. Yeah.
This
now.
one, could you see?
Yes, sir. Now.
So do you want me to keep the previous slide or this one? I don't know, nobody is talking, so I don't know what they are doing. When you are coming to class, are you looking at the screen or what are you doing? I don't know. Online classes are terrible. I don't know what is going on. I am doing my duty. So I am presenting my slides. Whether you are writing or what you are doing, that is up to you guys.
Can you show once the previous slide, sir? IAR.
Okay, are you able to see?
Yes, sir. Yes, sir. Done, sir. Next slide.
Okay, so one more slide and then I will stop today. So stability. So this point here, that the stability of a discrete time LTI system is equivalent to its impulse response being absolutely summable. This you have seen. When you did Bibo stability, you derived bounded input, bounded output stability by finding out the condition summation n equal to 0 to infinity or minus infinity to plus infinity, h of n whole mod less than infinity, or mod of hn is less than infinity. So that was the condition for the absolute summability of the impulse response. That is the condition for the before stability of a LTI system. I hope this has been taught to you in control systems. This definitely should have been derived. Right? Am I right? All of you have studied that addition?
Yes, sir. Yes.
So in this case, for a stable system, the Fourier transform of h of n converges, and therefore the ROC of h of z must include the unit circle. So we can try to combine the causality and the stability criteria. Initially, let me write this out, that an LTI system is stable if and only if the ROC of the system function h of z includes the unit circle mod of z equal to 1. So you see, this is if and only if. Okay. So it is possible for a system to be stable but not causal. Okay. That can also happen. System can be stable but need not be causal. So if you focus on causal systems, stability can easily be checked by examining the location of poles. For a causal system with rational system function, the ROC is outside the outermost poles. So the ROC must be including the unit circle, and it must be going beyond the outermost pole, that is outside the outermost pole. Mod z greater than the radius of the outermost pole, and that ROC must include the unit circle. That is a causal and a stable system. So you can have an anti-causal system and a stable system where the ROC is inside a circle, and that circle has a radius greater than 1, and the ROC includes the unit circle. So that is an anti-causal system but stable. But the causal and stable system must have an ROC flowing outwards from the outermost pole, and the outermost pole should be having a magnitude less than 1. That is the idea, if it has to be a stable system. Unfortunately, I cannot draw on a blackboard in online teaching and all, like it's too complicated. And I don't have any Wacom tablet or anything that I can use. So you'll have to think what I'm saying, and you'll have to imagine. Once you have finished, you let me know. So I hope it is done. Okay. So for the ROC to include the unit circle, all the poles of the system must be inside the unit circle. That is what I was saying. That the ROC has to be beyond the outermost pole, and the outermost pole has to be inside the unit circle. Then only it will include the unit circle. Okay. The region outside the outermost pole should include the unit circle. Pole has a magnitude less than 1, then it will include the unit circle. The ROC will include the unit circle. That is the ROC of a causal system and a stable system. So a causal LTI system with rational system function h of z is stable if and only if all of the poles of h of z lie inside the unit circle. That is, they must all have magnitudes smaller than 1. So you can have an anti-causal system which has its pole greater than 1. And that anti-causal system can be stable because the ROC will be a region like inside the outermost pole, or inside the innermost pole rather, and that will, if the innermost pole is greater than 1, then the unit circle is automatically included in the ROC. Therefore, you will have an anti-causal but a stable system. But if you want a causal and a stable system, then the maximum magnitude of the outermost pole has to be less than 1. So suppose you have a causal system with this system function a to the power n u of n, then it has this z transform like this. It has a pole at z equal to a. For the system to be stable, its pole must be inside the unit circle. You must have this condition, mod of a is less than 1. Then the ROC is mod z greater than a. If mod z is greater than n, then it includes the unit circle. So if mod a is less than 1, then if you integrate this a to the power n u of n, that is, you integrate summation n equal to 0 to infinity a to the power n with mod a less than 1, that will converge. That will converge to 1 by 1 minus a. So this is my last slide for today. So I hope all of you have attentively noted down things what I said today. A lot of concepts we came across, and we saw so many examples. So please work out more examples. And day after tomorrow we have the class test. So whatever I've taught till today is included in the syllabus for the class test. Okay. So you can expect questions up to this slide. So am I clear?
Yes, sir.
Okay, so if you have noted it down, then you can stop. And all of you, please check your mail for the link that I have given for accessing the Google folder. So familiarize yourself with that link.
Sir, shall we have numerical based questions?
Yes,
or
only numericals. Well, I think mostly numericals. Okay.
Oh, okay, sir.
So please work out problems based on these concepts, whatever I have taught, and the previous chapters, whatever I have taught. That is LTI systems, properties of LTI systems, BTFT, and Z transforms. That forms the syllabus for class test 1. I think next month you will have your midterm exam before the Dussehra holidays. So before 12th, next month you will have your midterm exam. I think all of you should start seriously prepared.
Hello, sir.
Yes.
Sir, what will be the total number of questions?
Why are you having so many curiosities? Let there be some suspense. Huh? I have not prepared the question paper. How can I tell you the answer? There is a 1 hour test. I cannot give you 10 questions, right? Just relax, prepare well. Okay, fine.
Sir?
Yes, yeah. Who is speaking?
Sir, can you tell us the process, like how we will be taking the test?
Nothing. I will show you the question paper. You will write the answer on a piece of paper. Okay. You keep a piece of paper in your hand and pen. No notes should be there with you. Everything should be kept away, and your camera should be on. All of your camera should be on. I should be able to see you, and you will write the answer on a piece of paper. I will keep the question paper like this visible to you. Okay. Just like I show the slides, I will keep the question paper like that. Then you just work out the questions, that's it. And you take a picture of that piece of paper, convert it to PDF and send it in the PDF file to me in the Google folder. Simple, huh? You understood, right? Whatever I said. I hope
Yes,
all,
sir.
It's very simple. There's nothing big deal. I hope all of you are doing similar things for your other class tests and all. Nah? Same thing is going on. Is it not? Other teachers also doing similar things. Because there will be problems, I cannot use Moodle. Moodle and all people use for objective questions. So here I have to see your answer. I have to correct it. There will be partial marks for the steps. So I have to think about how you have worked out the question. All that I will see. Okay, fine, everyone. So shall I disconnect?
Yes.
Okay.
Thank you, sir.